so let's define improper integrals of type 2. Let's see how to compute them. So first case, let's assume that f is fine. So from A to B it's fine, at B it's fine, A might be an issue. So, but not necessarily at x equals A. Then if I have the integral from A to B of f of x dx, that's the lesson we just had, so let me write it. I'm going to replace the issue point. I'm going to replace a by t. That's where there might be an issue. And then I have to send t to a to approximate this. But again, I want to avoid that problem at a, so I'm going to stay on the right of a, on the side of b. Second version, let's say A is continuous, but maybe not at B. So A is closed, B is not included in the interval. So this time, A is fine, so we leave it. B is not, so I'm going to replace B by T. And then I'm going to send T to B. But I want the interval from A to T to have no issues with F, so I don't want it to include B. So let me draw a picture from A to B. B is the issue, so let's pretend like it's an asymptote. I don't want to be taking T over on this side on the right of B because then my interval from A to B still contains B. So instead, I'm going to be taking my T to be less than B. So the interval from A to B has no issue. So that means B minus here. So if it's the bigger of the bound, you put a minus. If it's the smallest, you put a plus. But really, you're trying to avoid those endpoints and build a shorter interval. All right, and then in both cases, we'll say the integral converge if that limit gives you a finite number. We'll say it converges, or it exists, if the limit gives a finite number Alright, so that takes care of 2 points, 2 issues, the first point and the last point. But we still need to worry about points in between. So part 3. So assume that f is not continuous at C in AB. So somewhere in the middle, you have a vertical asymptote or any type of discontinuity, and assume further, well, if I'm going to look at the 2 parts separately. So if both integral from A to C and the integral integral from c to b converge, sorry, there's a dx missing, then the integral from a to b will be the sum. But as soon as one of them gives you infinity, minus infinity, or d and e, the whole integral will not exist. So if it doesn't converge, I'll say it diverges. So if one of them diverges, then the integral from a to b diverges too. Alright, so let's try one integral. Let's try the integral from 1 to cube root of x from 0 to 8. If you want, you can always stop the video and try it yourself before you look at my solution. That would be an excellent way of learning. First thing you have to do here is to figure out if you have an issue. If your function is continuous on the whole interval, then it's just FTC. You don't have to use improper integrals. So here, the denominator cannot be 0. And so that means cube root of x cannot be 0. So x cannot be 0. So at 0, I have 1 over 0, which doesn't exist. So I'm going to have an asymptote at x equals 0. So this is an issue, and it's the only issue I have, because for every other value, the denominator is not going to be 0, and I'm going to have 1 over a number, a non-zero number. All right, so I'm going to have, let's write it like this. I'm going to have to remove 0 and replace it by t. And then I'm going to take t going to 0. And since 0 is the smaller of the bound, I want to make it a bit bigger. So I'm going to put a plus here. Alright, so then I'm going to get the limit as t goes to 0 plus x to the minus 1/2 plus 1, 2/3, minus 1/3 plus 1, 2/3. I misspoke. Now I can use FTC because my interval has no discontinuity for a function. Then I'm going to plug in Alright, so 8, 1/3, that gives you 2, and then I square it, so that one is 4, and then I have 3 divided by 2, and then this one is, let me write it in 2 steps just to make it clear why that limit will work. So now I have a positive exponent, something like this. If I had a negative one, I would have 1 over 0, but now I just have 0 on top, and that's fine. It just gives you 0. So this part will give you 0, and so I'll get